Okay, so today I'm going to be just sharing with you all some of my experiences with IPv6. This seems to be a topic that, despite how long we've had IPv6 around, it still scares a lot of people, and a lot of deployments just haven't got IPv6 there yet. And so I'm going to go through sort of two stages. In the first stage, I'm going to do a really simple overview of IPv6 itself, including the addressing and subnetting at a very basic level, just to make sure that everyone's on the same page. And then in the second stage, I'm going to take a bit of a look at OpenStack itself in both the undercloud and in the application layer, and some of the areas where IPv6 is well supported or things to watch out for. So as a little history lesson, IPv4, which really is the internet as we know it today, was released in 1980. The addresses for IPv4 are 32-bit, which gives us approximately 4 billion addresses theoretically. It's still used for the majority of internet traffic today, and that 4 billion address limitation was foreseen even in the early 90s as going to become a problem. When you consider that the population of the world already exceeds that number, and we have more devices than we have people, you can see where that may become a problem. The initial IPv6 working group was formed in the early 90s. And in 1993, the IETF created an ad hoc working group to work on this area. And by 96, they'd standardized the protocol, which we now know as IPv6, which wasn't actually released until 1998. They expanded the address space significantly from 32-bit to 128-bit, which gives us a theoretical number of addresses that are far more than anyone should ever try and count to. Take 3, add 38 zeros to it, that's the number. In practice, the number is a lot less because of the address allocation practices, but that sort of helps. A lot of people wonder, why is it called IPv6? Why the number 6? What happened to IPv5? Well, IPv5, the version number comes from inside the actual IP packet. There's a version number field, and versions 0 through 3 were used for experimental versions of the internet before it really was the internet or ARPANET in the early days. IPv4 was the production one we had. Version 5 was used for a theoretical protocol called the Internet Stream, which never really reached production, and so that number 5 was already kind of used, so they just used number 6. So it doesn't really relate to the protocol so much as it was just the next number available. Looking at the rate of IPv4 resource allocation, this is a graph of the various regional internet registries and the number of IPv4 prefixes they have available for registration. And the majority of the regional registries have already hit their last /8 block of addresses. So that's like 1 dot anything in IPv4. The only one that hasn't run out is Afrinic, which serves the African region. They've got 1.5 of those /8 blocks available. So they're still allocating what they call a normal policy, where you can get any size sort of allocation that you like. But all the other regions that serve Europe, America, South America, and the Asia-Pacific region, they all have less than 1 available. And so what they now do is the maximum allocation you can receive is a /22, or 1,024 IP addresses. And you can see from this graph projections that even those allocations in North America, we've now already run out. They're completely gone. For Asia Pacific and Europe, they're running out. But any large organization, like if you want to be a public cloud, you cannot receive an allocation that would be big enough for you to use. It's only like a smaller organization, maybe a hosting company that could. And in those cases, there's now a secondary market for IPv4 addresses where you can buy addresses from organizations that already had them. Or in many cases, they would actually acquire large companies. So all the big cloud providers, a lot of them acquired some large, older companies that had very large IPv4 allocations, so they could ensure they had enough addresses to serve their customers for the coming years until we finally get around to a worldwide IPv6 adoption. I very naively did a presentation. IPv6 has been something I've been interested in for a long time. In 2003 at the Australian Linux Conference in Perth, where I stated that 2010 was a more likely period for IPv4 deprecation. How wrong I was, because it turns out that really 2010, this is a graph from Google of IPv6 the percentage of their users that have IPv6 available. And so in this graph, we can see that 2010 was pretty much where it started. Basically, no one had IPv6 2010, and it was only through the course of 2010 the first like 0.5% got online. But it is now rapidly increasing to the point that, according to Google's metrics, we have about a 20% worldwide connectivity with IPv6. It varies by country. Australia is less than 10%. The United States is much higher at sort of 30 to 40%. But on average, we can see that the adoption rate really is taking off now. So now is the time where really you need to start thinking about actually getting your networks connected, because we're actually going to have an IPv6 world. I don't want to predict the number because I was wrong 15 years ago, but we're getting there. The thing that really hindered this early on was uptake on CPE equipment, the customer connectivity. Most of the modems and such didn't have support. And also a lot of the ISPs, their devices were hardware-based routers already in the mid-2000s, and so that hardware did not have support for IPv6. Or they could perhaps software switch it, but then your performance was so low as to not really be worth it. I did notice here at the conference there is actually IPv6 on the Wi-Fi, but it's actually not a native IPv6 that's tunneled back to Hurricane Electric in the US, which is a fairly well-known provider where you can actually get a tunnel to set up IPv6 and experiment with it. That was very popular in the last decade. It's getting a lot more possible to get a connection to IPv6 now, depending on the country you're in. I'm curious, how many here are from Australia versus United States? So about half and half. So in Australia, it's still really hard, but in the United States, you got like a 50-50 chance at the moment. So to do a quick little review about number systems. If you understand this, that's great. I just want to make sure everyone's on the page. Looking at decimal numbers, which is the sort of the normal number counting system that we use whenever we talk about numbers, it's based on tens. And so when we write out a number, in this case I've written out the number 13, really what we're doing is placing numbers in columns to multiply out. So the first column is the number of ones, the second column is the number of tens, the third column is the number of hundreds, and so on and so forth in base 10. Another way we can look at this is with binary numbers. These are much more familiar to us in computers. As humans, we have 10 fingers. That's theorized as to perhaps why we count in a base 10 decimal. Computers mostly count in bits. Everything is either on or off, a 0 or a 1. So when we look at a number in binary, we have the same system of columns, but instead of counting in tens and hundreds and thousands, we go up by single numbers. We go 1, 2, 4, and 8. So in this example here, I'm showing how you would indicate the same number 13 in binary. And so we basically, in the same way here, would add 10 plus 3 ones to get 13. We have to add 8 plus 4 plus 1 to get 13. And so our binary representation of the same number is 1, 1, 0, 1. That'll come important when I talk about subnetting in a moment. Here's another example. We're going to move up the numbers a little bit from 13 to 113. To go to 113 in base 10 decimal is quite simple. We just add another 1, so it's 113. The number's not much bigger. But in decimal, we've got to add quite a few more digits because it's a more verbose notation for counting numbers. So in this case, we have to add 64, 32, and 16, plus one more. And so if you add those up, that gives you 113. So you can see that number's now very long at 1, 1, 1, 0, 0, 0, 1. So your binary is very verbose, takes up a lot of space. Your decimal's not too bad. When we look at IPv4 subnet numbers, they're composed of four numbers separated by a dot. We're all used to seeing these. Each of these sections can be a number from 0 to 255, which is 8 bits of information. And on the end, we then have a subnet mask. And so this is why I'm talking about binary, because that subnet mask tells us, if we look at that address as a binary notation, how many of the bits at the start of that address are part of the subnet or the network, and how many of those bits are part of the host or identify different hosts on that network. So in total with IPv4, we have 32 bits, and across the top here, you'll see 32 numbers. So when we say a /24, it's a very common subnet size we're used to seeing. That means that the first 24 bits are all unique to the network. And so every host on that network, those first 24 bits will be the same. And then the last 8 bits here, those are going to change to identify different hosts on the network. And so with IPv4, we have decimal numbered addresses, but we tend to use a binary number of bits for the subnet mask. Moving into IPv6, they opted to go with the hexadecimal notation. And hexadecimal notation actually increases the number of values we have in a single column. So with decimal, we've only got 10 values, 0 through 9. With hexadecimal, they augment that with 6 numbers, A through F. So what does this look like when we're looking at a number? Well, the number 9 still fits in a single column in both decimal and in hexadecimal. So in this case, in hexadecimal, the number 9 is represented exactly the same and there is no difference. What changes is when we go to 10. So when we look at the number 10 in decimal, it's now 1, 0. We've moved over to that next column, the 10. With hexadecimal, we can fit up to 16 values in a single column. So now at 9, the next number is A, and that stays in the same column. So the number 10 is represented simply as the letter A. If we want to look at a much bigger number with hexadecimal, and this is, you'll see in a minute, forms part of an IPv6 address, we could have the number 40AD, which in decimal would be 16,557. So you can see how that lets us compress that notation a bit. Instead of having 5 digits, we can now fit it in only 4, so it's a little more concise to look at on the screen. This probably looks familiar to most people because MAC addresses, we're used to seeing MAC addresses on Ethernet and wireless devices and Bluetooth. That also uses hexadecimal, but with only 48 bits as opposed to the 128 of IPv6. So here's an IPv6 address. It is definitely a little longer. This, I think, is sometimes why people get scared because they think, how on earth am I going to remember that address for every host on my network? Well, firstly, we're moving into the cloud era of everything being automated, so there's less and less we've got to remember, so there is some value there. That value did not exist 15 years ago. But there's also a few tricks we can use in order to simplify that address a little bit. The first trick we can use is the same as in IPv4, which is that we can delete the leading zeros. So instead of having 4 zeros, we can just collapse that down to 1 0. Or if a section is only 3 digits, such as the DB8 that you can see, we can just delete that leading 0. So already, just by deleting the repeating zeros, or leading zeros, you can see we've reduced that address to about half the size. That makes it a little bit easier to deal with. But there's an extra step we can take which we did not have in IPv4, which is that we can reduce multiple sections of only a 0 with a double colon. Now you can only do this once in an address, because if you did it more than once, you wouldn't know how many zeros were in each piece. But once inside an address, if you've got multiple sections with a repeating 0, you can collapse that up. So you can see here, the 3rd, 4th, and 5th sections were all 0. So when we simplify this address, we can then just put a simple double colon there. And now that address that was here is about 1/3 the size that it was before. So there's 2 little tricks we can use in IPv6 addressing to make those addresses a little more palatable to the human eye and to writing them out, hopefully with a keyboard and not by hand. By using a colon on the address instead of a dot raises a question. What if we want to put a port number on the address? Like 8080 for accessing a management service. Well, you can't really be sure because of that double colon notation. You're not really sure how many sections are in that address. So if we just put a port number on the end, there's no way to reliably determine was that a port number or was that simply the last portion of the address. So for that reason, if you're putting a port number with an IPv6 address, we enclose it like this with brackets around each end. And so the brackets signify the address portion, and then we're free to put the port on the end using the standard colon notation. This will work in a browser. Like this address is not valid, but if you type an IPv6 address into a browser, you use those brackets, you put the port, that will work. Do you want me to go back? You're good, all right. Much like in IPv4, I talked about that binary notation for the subnet mask. How many of the bits at the start of that address are identifying the network versus identifying the host? Well, we have much bigger subnets in IPv6. There's a lot more room than with IPv4. We're all squished in. And so what are the kind of sizes of subnets that we would expect to see? A /32 prefix on this first line that we can see, this is the size of subnet that will generally be allocated to a large internet service provider. And that allocation would then give that ISP a little over 65,000 /48 size prefixes, the next sort of major size down, that they could then allocate, and this is the expected allocation size to large organizations. Now this is where things have changed a little bit. In the early 2000s, when IPv6 was first standardized, they had this sort of panacea notation that we had so many addresses that we can just allocate hundreds of thousands of addresses to everyone. And the motivation behind that was, with IPv4, we've got a problem with routing table growth. We're now on the internet, and I haven't checked the numbers in the last couple of years, but it's well up over 500,000 or 600,000 individual network routes are now on the internet. And for hardware routers, that's a problem. It consumes memory, consumes CPU time to walk those tables, to look up the routes. So with IPv6, they wanted to try and reduce that. And the aim was, if you allocate a larger chunk of addresses up front, they're less likely to need to get a second or third allocation down the line because they received enough addresses in the first place. So in the initial standards, they suggested that basically everyone, even like a home network, should receive one of these /48 sized networks. That would give them 65,000 possible actual individual networks they could run. People realized, however, that probably, even though we've got all these addresses, all 38 zeros long of them, that really is quite wasteful, and you don't need to allocate 65,000 networks to home users. So that RFC was deprecated. So if you've heard about that, if you remember that information from the early days of IPv6, the current sort of recommendation for an end user site, I probably should have clarified, a /64, so this first half of the address, is pretty much the smallest size of a network, and I'll explain why in a minute. But so now the general recommendation is a /56 would give you 256 of these single networks, and that's probably the more ideal size to allocate to a home-style network, or even most businesses. But if it was a very large organization, maybe like the last presentation, someone like American Airlines, they would probably still get a /48, but your average small business is probably going to get a much smaller allocation like a 56. So this is one of the key changes that's come about in the last 10 years of IPv6. In 2011, specifically, that RFC was adopted for those new allocation sizes. We also have some special kinds of addresses in IPv6 that we didn't really have in IPv4. The first of such is link-local addressing. Now, we kind of have this in IPv4. If you've ever seen the 169.254 subnet, which is the zero configuration subnet, this was like an optional kind of subnet that you could use in IPv4 that you would only use if maybe there wasn't any DHCP server available. In IPv6, every interface always has a link local address that starts with FE80. They're automatically allocated using, in most cases, the MAC address of the interface. That's using a process called EUR64. And every interface always has this link local address as soon as it comes up. And even if it's assigned a real global address, it still maintains this link local address for a number of sort of internal IPv6 functions on the local network. I mentioned EUR64, and this is a way of turning the MAC address of an Ethernet interface. That MAC address is 48 bits. We need to expand that out to 64 bits to give us the other half of a network address. If you recall before, I said 64 bits is basically the smallest possible network size that we generally allocate to a network. Well, the other 64 bits can be auto-generated from the MAC address. And it's not really that important, but if you're always wondering, well, how does that happen? Basically what we do is first we take the MAC address. So here's an example of a MAC address. We need to pad that out from 48 bits to 64 bits. So we insert FE into the center, and that sort of pads it out. And then there's an extra bit within that address, which is designed to be set if the address has been automatically generated as opposed to manually generated by an administrator. And that bit needs to be flipped, which is why you'll notice even though the MAC address is FEC9, the actual IPv6 address we get is FCC9, and that's because there's that little bit flip that goes on. Your network interface will do that for you, so you don't need to worry about that. But the whole motivation behind that is if you wanted to manually assign an address like : 1, you're not going to conflict with these automatically assigned addresses because they're all going to have a little digit at the start that's going to push them into the upper half of that range. So keep them away from any manually assigned addresses that you configure. And so this EUI64 address is used for that link local address. That's how the system creates that. And it will also be used during address configuration that I'll talk about in a minute. Alongside those link local addresses, remember every single interface has a link local address. Well, we need some kind of equivalent if you want to have a private network. So if we've got an interface that's not publicly routable at all, perhaps a storage network, the equivalent to what we're used to using, like a 192.168, the RFC 1918 addresses, the IPv6 equivalent to that is called ULA, or Unique Local Addressing. The way this works is there's a special subnet set aside, which is, it starts with FD, and because it's a /8, it's only those first two letters that are significant for the network, FD. The 00 section is replaced partly with your network identifier. And the general idea is that you just completely randomly generate a number and add it on to that FD prefix. The idea behind randomly generating these numbers and not using the same networks is that if you had two large enterprises using these private networks and they then joined, if you've randomly selected one of these networks from, I think it's 1.1 trillion possible private networks you could have picked, it's highly unlikely that you had picked the same one, and therefore you'll be able to connect those internally and route between them without having to renumber everyone. So the RFC specifically states you can't pick a nice number, you can't spell coffee out in your personal prefix, that's frowned upon. I'm sure people still do it, I probably would. But there are a couple tools online you can use to randomly generate one of these networks. Here's one I generated yesterday. And by using those networks for those storage or other private networks, you know that you're not going to conflict with anywhere else in your organization, or at least it's highly unlikely. If you do end up conflicting, I'd suggest buying a lotto ticket. There was also another section of these addresses, instead of FD, FC, that was originally conceived to be like allocated by some kind of allocation authority, but that's never actually happened in practice. No one ever set up such an allocation authority, and so it's really just ad hoc. However, the 6XS organization / website does maintain like a registry of ULA prefixes people have picked to just kind of make it less likely you're going to use the same one as someone else. It's not in any way standardized, you don't need to use it, but the option's there if you want to put yourself in that list, but it's really not necessary. So in terms of comparing things that we know in IPv4, the first one of those would be ARP, or the Address Resolution Protocol. And this is the way on a network that we can find which IP address belongs to what MAC address. IPv6 has a very similar mechanism, which is called neighbor discovery. In IPv4, the ARP process happened as a broadcast packet, and it wasn't really an IP packet as such. It was a special kind of Ethernet packet that was broadcast to the entire network. In IPv6, they tidied that up a little bit. And so when doing these neighbor discovery requests, it actually uses that link local IP address that's automatically generated, and it uses that as the source of all of these neighbor discovery packets. And it also makes use of multicast in order as a target for these neighbor discovery packets. So instead of doing it as a broadcast for everything, they kind of cleaned everything up. They're using that link local address as the source, and they send it to a multicast address. So multicast is really built into IPv6 at its core. In terms of address configuration, or automatic address configuration, equivalent to DHCP for IPv4, there's actually really two methods primarily that this is done with in IPv6. The first of those methods is known as SLAC, or Stateless Address Auto-Configuration. This method uses that EUI64 process that I explained earlier to combine a router advertisement, so you configure your router to once a minute or a similar period, advertise to the network, here's the IPv6 prefix for this network. This is the one that was allocated to us by the organization or whatever. It then takes that and it combines it with its MAC address using that same EUI64 process to automatically assign it an IP address that will end up looking something like this. This is designed for like any network where you're just plugging your laptops in, or things that need outbound connectivity, not so much for servers where you want a reliable address that would change. In those cases, you might assign them statically. But this is sort of the primary way that most networks deploy their IPv6 setups. It's what you would have if you connected to the Wi-Fi network here. One of the early problems with this router advertisement process was there was no way to specify a DNS server. This seems to have been an oversight in the early design of the protocol. And this wasn't a super issue at the start because people were mostly running dual stack networks where you'd done DHCP, you got your IPv4 address, you got a DNS server, and then you got an IPv6 address as well. And you just used the IPv4 DNS server. There was no way to get an IPv6 DNS server initially. They did go ahead and fix that and updated the router advertisement specification to include a DNS server. So that is something that's now supported across all modern operating systems, which is good. However, people early on, they wanted to be able to configure DNS servers, but they also wanted to be able to assign a specific address. So they didn't want to deal with this EUI64 auto-generated address that they couldn't possibly type or remember. And so we do also have an equivalent to DHCP, which is surprisingly known as DHCP v6. It's a very similar protocol to DHCP v4. And it operates in much the same way. You have a DHCP server, you send out a request, you get a response, and you get assigned an address that most likely will be from a static pool. So it won't be one of those auto-generated addresses, it'll just be : 10 or 1A or whatever it happens to assign you. This is also helpful if you want to communicate some additional information, because those router advertisement packets don't support things like a TFTP server or an NTP server or some of these other options that we sometimes use. So a DHCP v6, we do have the option of including those servers. There's also a flag within the router advertisement portion that says, please use DHCP v6. So you can actually receive a router advertisement that says, please go and use DHCP v6 to configure this interface. And that can be done to basically automatically determine whether you should use DHCP v6 rather than doing it, like configuring your system to do it automatically. There's also a third special combination where you can auto-configure an address using Slack and get that EUI64 address, but then go to DHCP v6 not for an address, but just to get that additional information, to get the TFTP, to get the DNS, whatever it happens to be. That's a mode that's also available. Lastly, there's a special kind of DHCP v6 request called a PD, or prefix delegation. When you're on, this is more for the home network or broadband situation where you might have multiple actual networks at home. It's possible perhaps you had like a wired and a Wi-Fi or maybe a guest network. And so you need to receive your own /56 allocation that you can then assign subnets out from. In order to do that in an automated fashion, DHCP v6 PD is a way to, after getting your initial connection to the ISP up, which is only going to give you an IP address for your router itself and not one to then extend onto the local network, DHCP v6 prefix delegation lets you request that prefix from the ISP and then assign that to the local network. And that's a pretty common usage among any provider that's deployed IPv6 for end connections rather than data center connections. A few other little tidbits. NTU in IPv6 is a minimum of 1280 instead of the 576 it was in IPv4. And there's no fragmentation done along the path. So you can fragment an IPv6 packet, but it has to be done at the source host and it's reassembled at the destination. The routers no longer have to participate in this fragmentation, which is good for CPU workloads. NAT is generally not used in IPv6. There is now support in the Linux kernel for it. As of about 2012, it was added in 3.9 kernel, much to some people's distaste. But the general theory is that we shouldn't really need NAT because we've got enough addresses, and certainly we shouldn't be looking at dynamic NAT. In some cases, maybe like a one-to-one subnet NAT might make sense. I don't think it does, but some people think it does. But generally speaking, and this will go into OpenStack as I'll cover in a second, NAT is not really used. Another thing to think about in your deployments is single or dual stack. Do I deploy IPv4 and IPv6 to everything? The approach that some people are starting to take, and Facebook is most notable for this, is that their internal network, they've gone all IPv6, and they only terminate their IPv4 on the edge of the network, and all the back-end communication from their load balancers through application servers is all IPv6, just to simplify things. This works fine because you can send the v4 address sort of in the protocol headers or whatever. And it can sort of simplify that maintenance, but probably in most of the application deployments you'll initially do, you'll probably have a dual stack. So that's a general introduction to IPv6 itself. We've covered the addressing and the subnetting and kind of a bit about how it works. Now I'm just going to go through a little bit about OpenStack and the current support for IPv6 within OpenStack. The good news is that generally speaking, OpenStack has strong IPv6 support all the way through the stack. In Icehouse, a lot of it was already there, but a lot of features and little things were matured through the sort of Juno and Kilo timeframes. So really, you want at least Liberty, probably Metadata, to have like all of the features and all the bug fixes for most of that support. There's one small exception to this, which is Open vSwitch, which does not currently have support for doing the GRE tenant overlay networking between an IPv6 address like on the hypervisors. So you can have IPv6 in the tenant network and the VMs can be assigned them, but that overlay tunnel that runs between your hypervisors currently with GRE has to be an IPv4 address between each of the hypervisors. That was fixed in that you can now do a VXLAN or a Geneve tunnel over IPv6 as of Linux 4.3 and in Metadata. But if you're pre-4.3 or pre-Metadata, you would need to use IPv6 for your underlay network in the undercloud. One thing to note is that this can vary a bit if you're using like a third-party SDN or something. Like if you're using Neutron and the Open vSwitch agents, everything's fine. But if you're using like a Contrail or Cisco or someone's plugins, you'll need to check with them to see what their support is. And that can also apply to like even storage plugins and stuff. Maybe there's storage plugin from your vendor doesn't connect to IPv6 or something. So in those cases, you'd need to check. But most of the upstream support is pretty good. In terms of tenant networks, when we're creating networks for our tenants to use, because we don't have NAT, we don't have that same floating IP setup or private network setup that we're used to seeing in IPv4. So what we do with tenants is we actually allocate every tenant gets a globally unique IPv6 subnet that don't conflict. Now, it's still possible tenants could set up their own private networks with conflicting addresses, and that will still work. But when it comes to setting up routers or accessing the internet, we don't do that. We make sure we allocate a globally unique address to every tenant. How can we do that? Well, the first thing you'll want to do is set up a Neutron address scope. This is a concept that's not really that widely known yet. So if you don't know about address scopes, don't be surprised. You can look in the documentation. But an address scope basically means that all of the addresses within this scope are unique, so they should all be able to talk to each other without NAT. And you can actually do this with IPv4 as well. If you want to have multiple tenants set up using IP addresses that route directly and don't get NATed, you can use address scopes to achieve that with IPv4 and Neutron now. With IPv6, generally you want to set up a global address scope so that everyone, including the external and internal interfaces, are all in one scope so they can all communicate without any NAT. The second thing we want to do is set up a subnet pool. This is not quite as new as address scopes and can also be done in IPv4, but we can actually set up that pool. So that /48 allocation we got as an organization, you can give that to Neutron and tell it whenever a tenant asks for one, you can hand out a smaller section of that, a /64 to each tenant. And that can be done automatically with the subnet pools. So we set that up. You can see we specified that the overarching pool is a /48, but the size that we're going to allocate to each tenant is a /64. We also specify a couple extra little flags. One is --share, which says this is shared. That means any tenant and non-privileged, non-admin user can consume the subnet from that pool. And we can also set it as the default, so that if someone creates a v6 subnet without specifying the pool, that's just the one they'll get it from. You can also have multiple pools they can specify, but it's easiest just to use a single default pool in most applications. And then the last step is to actually create a subnet, and this is a step that the user can do, or the tenant can do directly as an unprivileged user, and they just do an OpenStack subnet create, and by default it's going to come out of that default pool, so they don't need to specify the subnet. OpenStack's going to specify it for them. There's two options in here you may not be that familiar with. The first is the IPv6 RA mode, and the second is the IPv6 address mode. So in this case, I've set them both to Slack, which means that we're going to use that automatic configuration. But Neutron does also support that DHCP stateful mode, where you assign an exact address that's not an auto-generated address. And it also supports that stateless mode, where it auto-assigns that EUI64 address, but it still runs DHCP-v6 to get maybe a DNS server or TFTP server or some other information. Both of those things can be done with Neutron. You can also specify just an RA mode of Slack and leave address mode out, which means it will allow the router advertisement packets out onto the network for an external router to handle, and Neutron won't be involved at all. You probably wouldn't, most people probably wouldn't use that setup, but it could be of interest to some. DVR, the distributed virtual router, and HA is one area where the support is a little weaker in that currently IPv6 with DVR is supported, but it runs through a central router, so it's not fully distributed like it is with IPv4. There's still work pending for that. And the L3HA version, where the subnets are moved from one router to another in case of a failover, there's no support currently for that with IPv6. Another possible way that we can get our external network outside of OpenStack to know which subnets are living within OpenStack is by dynamically telling the external network what subnets are now available. And so there's two ways currently that OpenStack supports to do that. I mean, the most simple way is that you just route that whole /48 at the Neutron router. Statically, you set that up. There's nothing dynamic about that. You can also set up BGP peering, so you can use BGP to get Neutron to advertise to the rest of your network what subnets are in use. And we can also use that DHCP-v6 prefix delegation. So Neutron can actually be a prefix delegation client and ask your external router outside of OpenStack for a prefix and then allocate that to the client. A couple of other little gotchas, Cloud Init and the metadata. Currently, the way Cloud Init works in most setups is it uses that EC2 compatible API, where it does a HTTP request to a special address of the 169.254.169.254. If you're doing an IPv4, IPv6 dual stack setup, that's fine, that metadata service is going to work. If you're doing an IPv6 only tenant deployment, they're not going to be able to contact that metadata service, and there's currently no equivalent special IPv6 address. The way that you can handle this in OpenStack is to enable the config drive feature, which is where that metadata, instead of being on a HTTP endpoint, is mounted as a drive to the VM, and Cloud Init fully supports that already. One concern with that used to exist was that you couldn't do live migration, because this was mounted as a CD-ROM to the virtual machine, and that prevented live migration. That's been fixed in more recent OpenStack versions, and you can now specify that config drive as a VFAT, or basically a FAT file system, and that gets around that live migration limitation. One last little thing to be aware of is reverse DNS. With IPv4, it was easy for us to generate our reverse DNS zones because we only had a few hundred or few thousand addresses. With IPv6, we've got these huge subnets, and generally speaking, we still need to generate reverse DNS if you're using applications that might need it. The biggest one is email. If you want to send email, and Google, for example, Gmail, they host a significant portion of enterprise email. If you try to send them an email over IPv6 and you don't have reverse DNS, they'll just outright reject it with that question. So if you're sending email direct from your instances, you want to look at ensuring you have reverse DNS automatically generated. If you don't, then it's not maybe as big a concern, but email's the number one thing where you've really got to make sure that that reverse DNS is set up. And it'll surprise you because you'll have added IPv6 and suddenly your email stops getting delivered because using Slack, every machine on your tenant network will automatically get an address. So you've got to be aware of that. So that's covered off IPv6 and OpenStack, and that's basically all the content I have from you. However, if any of you have some colleagues maybe that still aren't convinced, and I've had a few that really love entering numbers on their IP addresses on their number pad, I have available a few of these IPv6 Buddies, which is a USB number pad with hexadecimal and a double colon to make convincing your coworkers that IPv6 is much easier to deploy than they previously thought. So if anyone has some great questions or any good reason they would like this, I've got a few of these to give away, and I'd be happy to take any questions. Sure. So the question is there a roadmap or spec for the DVR and HA side of things? There were specs created a couple of years ago that then stalled and don't have any progress. I double-checked that last night, and from what I could see, there's not any current work on the DVR or HA side to improve that support that's currently undergoing, as best I could tell. And the last couple releases in Newton and a Carter, there's not been any real big IPv6 changes. So the question is, would the preferred method be to use BGP to advertise those? I'm really not sure what the preferred method people are using is. I also don't know if it would really solve, I guess it partially solves that problem, but if that would be more for the HA side that you would need the BGP. The DVR side, I guess that probably would be the way to go. Yeah, that's a good question. So probably using that BGP to advertise it, so if your router gets rebuilt to another router, that it just works. You don't have to manually reconfigure stuff. Please come see me. I'll happily give you IPv6 Buddy. Do we have any more questions? We've got a microphone here as well.
I don't need it. Do you have any idea how many pure IPv6 OpenStack installations there are? And is there a reference architecture?
So, yeah, so the question is, do I know how many pure IPv6 OpenStacks there are, and is there a reference implementation? I do not know the number, and there is documentation about doing IPv6 in the various OpenStack guides, and I know it's possible. For example, we've got some bundles with Juju that we use at Canonical that will do a pure IPv6 deployment that does work, but I'm not aware of any people advertising that they've done a pure v6 implementation. And a couple of people I heard that wanted to do it hit issues like I talked about where they wanted to use a third-party SDN that maybe it didn't fully work. But yeah, so unfortunately I don't have good news.
I worked for DreamHost and it was my vision.
Right, okay,
Exactly
understood.
And we came up against a number.
Right, and wrote your entire own networking stack. Yeah, great. Please come see me. Any further questions? I'd love to get the microphone over to you.
That's right, only question. Do you know if the NBN CPE is supporting IPv6?
Australian only question, does the NBN CPE support IPv6? That's a great question, and I don't know the exact answer to that, but most modern CPE shipping now does support it. And the NBN side of stuff, you still have a separate router usually, so the answer is probably, but it's the NBN, so we don't really know. Any further questions?
Yes. On an internal network, we're using internal BGP. Is there a way of trying to manage in the autonomous zones for this to work? Or how are you getting that part of that BGP functionality to work?
In terms of like auto-allocating an AS number?
Yeah,
or
correct.
I don't think there's like an auto-allocation policy or anything. I think you just set it when you do the BGP configuration with Neutron, you just tell it like what AS number to use, as best I'm aware. So I'm not aware of anything like for managing that.
Thank you.
Yes.
One of the missing gaps that you mentioned is related to the HA routers. Can you please elaborate on what is currently missing in that?
So the question was about the HA routers, and what did you want me to elaborate on, sorry?
Yeah, like what is the piece that is actually missing for the HA routers?
Right, I haven't checked into that fully to code level, but my assumption would be the HA router implementation uses KeepAliveD to do like the failover. My assumption would be it currently just doesn't have support for writing a config out for KeepAliveD. And actually now that I think about it, I have no idea whether KeepAliveD itself supports IPv6, because I've never tried. It may do. So I'm guessing that's the missing piece. If you want to know more about that, I'd be happy to talk to you afterwards and we can check the code and find out.
Just so as well, there's actually a bug. There's actually currently a bug with the DNS mask configuration that's generated if you've got DHCP v6 enabled. So one of my colleagues is working currently on getting that sorted out.
Okay, so there's a bug with the DHCP v6 config?
For DNS mask.
Okay. Yes, question?
Not a question so much as a statement. If anybody wants to talk to the Neutron guys about particular things that you want to see for IPv6, there's a forum session tomorrow at 2:40 up on the 4th floor. It's called Neutron Pain Points. We're going to schedule you to go and ask your questions of them.
Okay, so the point raised tomorrow at 2:40 p.m. There's a Neutron Pain Point session. So if you'd love to talk to the Neutron team about IPv6, that'd be a great session. So I think I'm out of time now, and I think it's break time, but I'd be happy to answer any more questions up the front here afterwards. So if you'd like to come claim your IPv6 buddy from asking a question or asking me any questions, please come up. Otherwise, thank you very much for listening. I really appreciate it.